On Monday, an asteroid between 50 and 100 feet across passes Earth at about 56,700 miles, a quarter of the distance to the Moon. Its name is 2026 JH2, and a week ago it did not have a name because nobody knew it existed. It was found days before arrival, and it is not alone. This is one of the most crowded weeks of asteroid flybys on record. In the next few minutes, you will understand exactly why we found it this late and what that means for the next one. 3 days from now, on Monday, May 18th, an asteroid somewhere between 50 and 100 feet across is going to pass between Earth and the Moon. It has a name, 2026 JH2, and here's the first thing you need to know about it. A week ago, that name did not exist. Nobody had cataloged this object. Nobody was tracking it. It was found days before its arrival, and it is now confirmed on a path that brings it closer to Earth than the Moon. Let me give you the number that matters. At its closest approach, around 21:23 Universal Time on Monday, 2026 JH2 will be approximately 56,700 miles from Earth. To put that in context, the Moon sits at an average distance of about 238,000 miles. So this object is passing at roughly a quarter of the distance to the Moon. It is crossing well inside the lunar orbit. It is even passing closer to Earth than a large share of the satellites we depend on, because the ring of geostationary satellites, the communications and weather satellites, sits at about 22,000 miles up. In 2026, JH2 threads through at 56,000. This is not a distant speck. It is a close pass. By any reasonable definition of close, there's no confirmed impact threat here, and I want to be clear about that up front. The orbital math says it misses, but the story is not really about whether this one rock hits us. The story is about how we found it, when we found it, and the fact that 2026 JH2 is not arriving alone. Because it turns out this is one of the busiest weeks of asteroid flybys on record, and once you understand why that matters, this stops being a routine space headline and becomes something worth your full attention. Here is the profile of this object, and every number in it comes from NASA's Jet Propulsion Laboratory and the Global Tracking Network. 2026 JH2 is estimated to be between 50 and 100 feet across, which is roughly 15 to 30 meters. I need to be honest about that size figure because it is not a measurement. Nobody has bounced radar off this object yet. The size is calculated from how bright it appears and an assumption about how reflective its surface is. That is the standard method for a freshly discovered asteroid, and it always comes with a wide margin until better data arrives. So when you hear 50 to 100 feet, what you are really hearing is a best estimate based on a faint dot of reflected sunlight. The object is moving relative to Earth at about 9 kilometers per second. That is roughly 20,000 miles per hour. By the standards of near-Earth objects, that is actually on the gentler end of the scale, but it is still a serious closing speed for a serious chunk of rock. 2026 JH2 is classified as an Apollo-class near-Earth object. That means its orbit around the Sun crosses Earth's orbit. Picture our planet's path as a lane on a track. Most asteroids stay in their own lanes, far away. An Apollo-class object does not. Its path swings across ours. And that matters, because the Apollo class is the most populous of the orbit types that can actually intersect Earth, and it is the class responsible for most of the close approaches and most of the actual impacts in our planet's history. 2026 JH2 is not some exotic outlier. It is a very ordinary member of the single most consequential population of rocks in the inner solar system. So who found it? The discovery came from astronomers working across several facilities, and 2 of them are worth naming. One was the Farpoint Observatory in Waubonsee County, Kansas. The other was the Mount Lemmon Observatory in the Santa Catalina Mountains, north of Tucson, Arizona. These are working observatories, part of the network of telescopes that scans the sky every clear night looking for exactly this, faint points of light that move since the night before. They caught it, they reported it, the orbit got calculated, and the result was a confirmed close approach just days away. One more number worth holding on to because it explains the late discovery as much as anything else. The brightness of this object, what astronomers call its absolute magnitude, is around 26.2. In plain terms, that is faint. It is far below what the human eye could ever register, and it is faint even for the survey telescopes built specifically to hunt these objects. A rock this size only crosses into the detectable range when it has already come close. And close, in this case, meant days from arrival. So the profile of 2026 JH2 is a small, dark, fast-moving faint object on a crossing orbit, discovered at the last reasonable moment. Every part of that description is ordinary for its class. None of it is a special case, and that is exactly why it is worth a closer look. Sit with the timeline for a second, because it is the thing that turns this from a footnote into a story. The headlines are calling 2026 JH2 a newly discovered asteroid. And that word newly does not really land until you understand what it means. It does not mean discovered last year and refined recently. It means discovered essentially now, right before arrival. From first detection to Monday's closest approach is a window you could count on one hand. And here is why that should get your attention. There is no confirmed impact threat from this object. That is true. But if 2026 JH2 had been on the trajectory that ends here instead of the one that slides past us, the warning would have been exactly the same. The same handful of days. The discovery did not happen late because somebody made a mistake. It happened days out because that is how the system works for an object this size. The way these objects get found explains the whole thing. An asteroid like this does not glow and does not transmit. It is a dark rock reflecting a little sunlight, and from Earth it shows up as nothing more than an extremely faint dot in a field of millions of dots. The way a survey telescope finds it is by photographing the same patch of sky over and over, minutes apart, and letting software flag the dots that move between frames. Stars do not move, an asteroid close to us does. Once enough of those position measurements pile up, the orbit can be calculated, and only then does anyone know how close it will come and when. Every step of that chain depends on the object being bright enough to register in the first place. 2026 JH2 was simply not bright enough, not close enough, to be detectable until it was nearly here. That is not a failure. That is the system performing exactly as designed, and that should bother you more than a failure would. Now, 50 to 100 feet. And you might hear that and think, that is small, that is basically a non-event. Resist that. An object in this size range is not a planet killer. It would not end civilization, but it is very far from harmless, and we have a recent concrete example of exactly what a rock this size can do. In February of 2013, an object roughly 60 feet across came in over the Russian city of Chelyabinsk, right in the middle of the size range we are talking about for Monday. It did not even reach the ground. It exploded in the air, what we call an airburst, and that airburst released energy estimated at 400 to 500 kilotons of explosive force. The shockwave from that blast spread out and blew out windows across 6 cities. It injured around 1,500 people, and nearly every one of those injuries came from flying glass, because people saw the brilliant flash in the sky and went to their windows to look, and they were standing at the glass when the shockwave arrived and shattered it. There is a bigger event worth knowing about too, because it sets the upper edge of what this population can do. In June of 1908, an object somewhere around 160 to 200 feet across came down over Tunguska in remote Siberia. It also exploded in the air rather than cratering, but its airburst carried energy in the range of several megatons up to over 10 megatons, and it flattened an estimated 830 square miles of forest. The only reason Tunguska is a scientific curiosity instead of one of the worst disasters in recorded history is that it happened over empty wilderness. Geography decided the outcome. Not any warning system, because there was no warning system. That is the ceiling for the kind of object we are discussing, and it is not far above the regional devastation class that our catalog is only 40% complete on. So this is the reference frame for Monday's object. Not the end of the world, but a city's worth of broken windows and 1,500 injuries from a rock the same size as the one passing us, and that one never even touched the surface. And here is the part that connects straight back to the discovery problem. The Chelyabinsk object was detected by no one. Not a single telescope caught it before it entered the atmosphere. The warning time was 0. It came in from the direction of the sun, out of the daytime sky, and our telescopes physically cannot look there, because the sun's glare drowns everything out. So 2026, JH2, which we did catch, days out, is actually the good version of this, the version where the system worked. And the good version still only gave us days. Here is where this stops being a story about one asteroid. 2026, JH2 is not arriving alone. In the same stretch of days, the public asteroid tracking lists, the close approach tables built from JPL's data, have lit up with an unusually crowded set of entries. Not one object passing inside the moon's orbit this week, around 8 of them. Let me give you the baseline so that number means something. A single asteroid passing inside the Earth-Moon distance is common. It happens many times a year. It is not news on its own, but roughly 8 of them inside a single week, with several passing within a day or two of each other, is on the high end of what the people who watch these lists closely tend to see. This is a genuinely crowded week, so what is in the wave? They are all small near-Earth asteroids, the same general population 2026 JH2 belongs to, and most of them carry similar designations. because they were all found recently. There is 2026 JK2, an object around 26 meters across, roughly 80 feet, making its closest approach yesterday at about 1.24 lunar distances and moving fast, around 20.5 kilometers per second. There's a string of others with designations in the same series, most passing within or just beyond 1 lunar distance across this week. And 2026 JH2 sits at the close end of that whole group, one of the nearest passes of the entire wave. When you take the orbits of this cluster and plot them together, something interesting shows up. Out at their far points, away from us, these orbits look nothing alike. Different shapes, different sizes, different tilts relative to the plane of the planets. By every measure, out there, these are unrelated objects on unrelated paths, but follow them inward, toward Earth, and they converge. The paths draw together and crowd into a tight region right at Earth's orbital path. There is a pattern inside that convergence worth noting. The objects in this group that pass closest to Earth tend to be the ones moving more slowly relative to us on flatter orbits. The ones that pass at a greater distance, like 2026 JK2 with its high speed and steep tilt, tend to be the faster, more steeply inclined ones. A slow, flat object travels almost alongside Earth and can ease in close. A fast, steeply tilted one punches through the neighborhood at an angle and is gone. Now, I want to be straight with you about how to read this, because there is an honest objection here. Part of the reason these orbits all seem to converge on us is simply that we only found these objects because they came near us. If the only rocks you ever detect are the ones that pass close, then naturally every rock you have detected passes close. That is real, and it has to be subtracted out before anyone gets excited. But it does not explain everything. It does not explain why this particular week is so crowded, and there is genuine physics, the gravity of Earth, and the other planets, focusing the population of nearby objects, by which small bodies really do group up in ways that are not an illusion. So the honest read is this. The convergence is partly an artifact of how we look and partly real. And either way, the wave does one thing that is not in dispute. It is 8 rocks we could see this week, and it makes the detection problem impossible to treat as abstract. Here is the uncomfortable context behind everything I have told you so far. We do not have a complete map of the objects in our neighborhood, not even close. What we have is a catalog, and that catalog has 3 very different levels of completeness depending on size. For the largest objects, the true civilization enders, 1 kilometer across and up, the catalog is believed to be more than 90% complete. That is the good news, and it is real news, so take the win. We have found the overwhelming majority of the objects big enough to end us. We know their orbits, and none of the known ones are coming for us. The middle tier is the regional devastation class, objects around 140 meters and up. Not planet killers, but big enough to erase a city or generate a tsunami. NASA was given a goal to catalog at least 2/3 of these. That goal has not been met. The most recent figures put the fraction actually found at roughly 40%. So for the class of object that could take out a metropolitan area, around 6 in 10 are still unknown. And then there is the bottom tier, the one 2026 JH2 belongs to, the tens of meters class. For this size, the catalog is not 40% complete, and it is not 90% complete. It is a few percent, or less. The reason is simple physics working against itself. Smaller objects are fainter and harder to see, and there are vastly more of them than there are big ones. The objects that are hardest to detect are also the ones there are the most of. So the overwhelming majority of rocks in 2026 JH2 size range are simply unknown until they are close enough and bright enough to trip a survey telescope, and that usually means days of warning. And sometimes, like Chelyabinsk, it means none at all. So say the warning is real one day. A survey telescope catches a faint moving dot, the orbit gets worked out, and the answer comes back that it does not miss. The detection worked. Now the only question that matters is what we can actually do. And the honest answer is almost nothing, and it gets worse the more you understand it. Here's what we do have, and it is genuinely impressive. In 2021, NASA launched a mission called DART, the Double Asteroid Redirection Test. The plan was to fly a spacecraft into an asteroid on purpose and see if the impact would change its orbit. The target was a small moonlet called Dimorphos, orbiting a larger asteroid called Didymos. In September of 2022, the DART spacecraft slammed into Dimorphos at thousands of miles an hour, and it worked. The impact measurably shortened the moonlet's orbit around its parent. DART proved something that had only ever been theory. It proved a kinetic impactor. The thing you crash into another thing can actually change an asteroid's path. But here is everything DART was not. It was one test, against one carefully selected object, chosen specifically because its setup made the result easy to measure. It was planned over years. A real threat would not come prepackaged for easy measurement, and there is no standing, ready-to-launch deflection system built on top of that one proof. DART showed the principle works. Nothing operational has been built behind it. It is the equivalent of proving water puts out fire in a lab and then never building a fire department. And the physics makes the gap worse. A kinetic impactor does not stop an asteroid. It changes the asteroid's speed by a tiny amount, and that tiny change compounds, orbit after orbit, until it grows into the difference between a hit and a miss. The nudge is small, time is the multiplier, which means the whole strategy needs years of lead time to be reliable. Now line that up against the warning times we have been talking about. Days for an object the size of 2026 JH2. The one tool we have proven works needs years of runway. The detection system for small and medium objects frequently gives us days to months. The tool and the warning do not fit together. And before you ask, no, you cannot just blow it up. Shattering an incoming object turns one impact you can model into a cloud of fragments still heading down the same path. Every serious method in the Planetary Defense Toolkit depends on lead time, and lead time is exactly the thing we do not reliably have for objects this size. It does not have to be this way, and there is one object that proves it. Apophis is a much larger near-Earth asteroid, several hundred meters across, headed for a very close, but by current calculation, safe flyby in 2029. Apophis is not a surprise. We have known about it for years, tracked it, refined its orbit over and over. And because we have known for years, if the math had come back differently, we would have had the years of runway a deflection mission actually needs. The difference between Apophis and 2026 JH2 is size. Apophis is big enough to catch early. 2026 JH2 is small enough to live in the part of the catalog that is nearly empty. Same system, two opposite ends. So here is where things actually stand. On Monday, 2026, JH2 passes Earth at about 56,700 miles, a quarter of the way to the Moon, and it misses us. That part is settled. If you want to watch it, the Virtual Telescope Project has announced a live online observation of the encounter. By Tuesday, it will be gone, back into the dark. But the things to actually watch go beyond Monday. Watch the close approach tables over the next week because this wave is not finished. And the count of objects passing inside lunar distance is the clearest signal we have of how crowded our neighborhood actually is right now. Watch for radar observations of 2026 JH2, because if a radar facility gets a return, that loose 50 to 100 foot size estimate will tighten into a real measurement. And watch the bigger picture, the slow progress on new detection capability, because the entire problem this flyby exposes comes down to one thing. The detection half of planetary defense, incomplete as it is the half that works and is improving. The response half, the ability to take a warning and do something with it, effectively does not exist beyond a single successful test. 2026 JH2 is safe. The honest takeaway is not that it is safe. The honest takeaway is that safe this time was the trajectory, not anything we did. And the few days of warning we got would have been the same few days if the answer had been different. We found this one. That is the good news. What we could have done about it is the part still waiting to be built. We will be tracking this as it develops.